Random forest is an ensemble learning method used for both classification and regression tasks. It operates by constructing a multitude of decision trees during training and outputs the mode of A. Classes. For classification, auth mean prediction. For regression, of the individual trees. The key idea behind random forest is to reduce overfitting by averaging the result of multiple decision trees, each trained on different subsets of the data. Bootstrapping. Random forest creates multiple subsets of the original dataset using bootstrapping, which means sampling with replacement. Each subset trains one decision tree, ensuring diversity. Feature randomness. During each split in a decision tree, random forest only considers a random subset of features, which reduces correlation between trees and increases robustness. Voting and averaging. For classification tasks, the final prediction is the majority vote across all trees. For regression tasks, it's the average of all tree predictions. Out-of-bag score. Each tree is trained on a bootstrapped sample, leaving some data out. These left-out samples are used to calculate an out-of-bag error, giving an unbiased estimate of model performance. Feature importance. Random forest calculates how much each feature contributes to reducing impurity across all trees, helping to identify the most important features in the dataset. Reduces overfitting. Unlike a single decision tree that easily overfits, combining multiple trees smooths predictions, reducing variance and making random forest more generalizable. Handles missing data well. Random forest can maintain accuracy even when some features are missing by averaging across different trees, each trained on different subsets of features. Works for classification and regression. Random forest is highly versatile, capable of solving both classification and regression problems effectively. Let's understand the random forest classifier with a simple example where we want to classify whether a fruit is an apple or an orange, based on two features, weight and color. In the first step, we create multiple subsets of the dataset by sampling with replacement. For simplicity, let's create two subsets. For each subset, we build a decision tree. Each tree uses a different feature or condition to split the data. Let's say tree 1 is built from subset 1 and tree 2 from subset 2. Now, suppose we have a new fruit with weight 145 grams and color 0. Let's see how each tree classifies this new point. Since both trees predict orange, the final prediction by the random forest classifier is orange. In a random forest for classification, ties can occur when two or more classes receive the same number of votes from the individual decision trees. The algorithm uses tie-breaking mechanisms to resolve such conflicts. There are several mechanisms to resolve ties in a random forest. Let's explore them one by one. Random selection. If there is a tie, the algorithm randomly selects one of the tied classes as the final prediction. Class prior probabilities. If class prior probabilities are known, the class with the higher prior probability is selected. Weighted voting. If the random forest uses weighted voting, the class with the higher total weight is selected. Default class. In some implementations, a default class is chosen in case of a tie. Let's revisit the fruit classification example. Suppose we have 4 decision trees, and their predictions for a new fruit are as follows. Here, tree 1 and tree 2 predict orange, while tree 3 and tree 4 predict apple. This results in a tie. 2 votes for orange and 2 votes for apple. To resolve the tie, the random forest uses one of the tie-breaking mechanisms. Let's explore how each mechanism works. The simplest mechanism is random selection. The algorithm randomly picks one of the tied classes, such as orange or apple. If the class prior probabilities are known, the algorithm selects the class with the higher prior probability. For example, if apples are more common, it predicts apple. In weighted voting, the algorithm considers the confidence of each tree. If trees 1 and 2 have higher confidence for orange, it predicts orange. Some implementations use a default class. If apple is the default, it predicts apple in case of a tie. If the random forest outputs class probabilities, the tie can be resolved by selecting the class with the highest average probability. Here, tree 1 predicts orange with 70% probability. Tree 2 with 60%, tree 3 predicts apple with 60%, and tree 4 with 70%. The average probability for orange is 0.5, and for apple is also 0.5. In this case, the tie remains unresolved, and another mechanism must be used. In conclusion, while tie-breaking mechanisms are important, they are rarely needed in practice because random forests typically consist of hundreds or even thousands of decision trees, making ties extremely unlikely. Let's take a deeper dive into how random forests work their magic in classification tasks. At the heart of this process are 2 key mathematical concepts, Gini impurity and information gain, that guide the construction of decision trees. By understanding these, along with the ensemble power of random forests, we'll uncover why this technique is so effective. Imagine we're classifying fruits, say, apples versus oranges, based on features like weight and color. Let's explore how these ideas come together step by step. First up is Gini impurity, a measure of how mixed or impure a set of samples is. Picture a node in a decision tree containing a mix of apples and oranges. If every fruit in that node is an apple, the Gini impurity is 0. It's perfectly pure. No confusion. But if it's an even split, half apples, half oranges, the impurity peaks. signaling maximum uncertainty. The formula for Gini impurity is Gini equals 1 minus the sum of squared probabilities for each class. Let's apply this to an example. Suppose our dataset has 3 fruits, 2 apples and 1 orange. The probability of apple is 2/3, and orange is 1/3. Plugging in Gini equals 1 minus 2/3 squared plus 1/3 squared, which simplifies to 4/9, or about 0.444. Now, building a decision tree isn't just about measuring impurity. It's about reducing it. That's where information gain comes in. It tells us how much cleaner our data gets when we split it based on a feature, like weight less than or equal to 155 grams. For our example, splitting on weight less than equals 155 gives us 2 pure child nodes. One with just an orange and another with 2 apples, both with Gini impurity of 0. Information gain is the parent Gini minus the weighted average of the child Ginis. Here, it's 0.444 minus 0. So 0.444. The maximum possible gain, meaning this split perfectly separates the classes. You might ask, why use Gini impurity over entropy? Gini is simpler and faster to compute, without logarithms, making it efficient for large datasets. It also tends to favor balanced splits. A single decision tree can overfit memorizing noise in the data. RandomForest solved this by building many trees, each on a random subset of data and features, and averaging their predictions. This randomness ensures that each tree is slightly different, reducing overfitting. When combined, their diverse perspectives lead to a more robust and accurate model. In summary, random forests use Gini impurity to measure node purity, information gain to choose the best splits, and an ensemble of diverse trees to make robust predictions. RandomForest Regressor is an ensemble learning method used for regression tasks. It operates by constructing a multitude of decision trees during training and outputs the mean prediction of the individual trees. The key idea behind RandomForest Regressor is to reduce overfitting by averaging the result of multiple decision trees, each trained on different subsets of the data. Let's understand the RandomForest Regressor with a simple example where we want to predict the price of a house based on 2 features: size and location. In the first step, we create multiple subsets of the dataset by sampling with replacement. For simplicity, let's create 2 subsets. For each subset, we build a decision tree. Each tree uses a different feature or condition to split the data. Let's say tree 1 is built from subset 1 and tree 2 from subset 2. Now, suppose we have a new house with size 1450 square featuring in location 0. Let's see how each tree predicts the price for this new point. The final prediction by the random forest regressor is the average of the predictions from both trees, which is $255,000. Let's explore the advantages and disadvantages of the random forest algorithm. Here is a table summarizing the advantages and disadvantages of random forest. Random forest achieves high accuracy by combining predictions from multiple decision trees. However, it can be computationally expensive, especially with a large number of trees. Random forest reduces overfitting by averaging predictions from multiple trees. However, it may still overfit on noisy datasets if not properly tuned. Random forest handles missing data well by averaging predictions across trees. However, imputation may still be needed for optimal results in some cases. Random forest provides feature importance scores, helping identify key features. However, feature importance can be biased for high cardinality features. Random forest works well for large datasets with many features. However, training time increases with more trees and features, making it less scalable for very large datasets. Random forest is more interpretable than some black box models like neural networks. However, it is less interpretable than a single decision tree due to its ensemble nature. This concludes the discussion on the advantages and disadvantages of random forest. Random forest is an ensemble learning method that builds multiple decision trees and combines their predictions. It is widely used for both classification and regression tasks due to its robustness and accuracy. Let's explore its working, advantages, and limitations. Here is a summary table highlighting key aspects of random forest, including its algorithm, key concepts, strengths, and weaknesses. Random forest is an ensemble algorithm that builds multiple decision trees using bagging in feature randomness. Each tree is trained on a random subset of the data and features, ensuring diversity. The key concept behind random forest is to reduce overfitting by averaging predictions from multiple trees. This makes the model more robust and generalizable. Random forest is widely used for classification, regression, feature importance, and outlier detection. It is versatile and performs well in many real-world applications. Its strengths include high accuracy, the ability to handle missing data, and robustness to outliers. It is also less prone to overfitting compared to single decision trees. However, random forest can be computationally expensive, especially with a large number of trees and features. It is also less interpretable than a single decision tree due to its ensemble nature. To optimize random forest, it is recommended to tune the number of trees, limit the depth of individual trees, and use feature selection to reduce training time and improve performance. In conclusion, random forest is a powerful and versatile algorithm that combines the strengths of multiple decision trees. It is highly accurate, robust to overfitting, and capable of handling complex datasets. However, it requires careful tuning and can be computationally expensive. By following best practices, random forest can be effectively used for a wide range of machine learning tasks. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up. Subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.